Dear users of this video, on the example of laser marking technology, we will consider the calculation approach, an approach applicable to all unestablished and unoptimized technological modes. Professor Nikolai Tonchev is the creator of this presentation. He is a professor of modeling, analysis, and optimization of technological processes, and I am his assistant. Professor Nikolai Tonchev is the author of a trademark registered in the Patent Office in Bulgaria, the essence of which is the principle of the moving constraint method introduced by Professor Stoyan Kolev-Stoyanov. The differences in the approach we are going to comment on and the original idea of the moving constraint is that now it is possible to use several constraints at the same time with a variable step between them. Thus, analysis and optimization become very friendly and the expected decision is quickly taken. An object of research was chosen, laser marking, a technological process characterized by the simplicity of its two controlling factors, and also that it is a modern technology, as well as for the reason that the example is very spectacular due to the fact that it is related to multiple images. Let us now turn our attention to the quality of the images obtained in different technological modes, defined as a combination of the power of the mode and the speed of the laser beam in image formation. To all these 9 combinations between the power, normalized in percentages, and the speed, expressed in millimeters per second, corresponds the time to obtain an image of the corresponding quality. For the values of the criteria marked in the table, it is clear that their maxima are at different control parameters, which justifies the application of an optimization maxima which justifies the application of an optimization procedure for determining the rational mode. This is how we reach our goal. With this presentation, we seek to define a technological mode as a combination of the input parameters that guarantees an acceptable image quality obtained in a relatively minimal time. This will be accomplished using different weighing factors for the criteria and with different optimization strategies. The formulated problem falls under the nonlinear bicriterial optimization, defined by two nonlinear regression models describing the time and quality criteria. The problem is also defined as two-dimensional based on the two controlling technological factors. To define the problem, it is necessary to derive the models from the table of combinations, one for the time of image formation and the second for the quality of the image. Both models are a function of the control input parameters, namely the normalized power and beam speed at marking. The derivation of the regression parameters is guided by a standard statistical procedure, the calculations of which are shown here. According to the expected structure of the model, a matrix is formed based on the combinations of the design of the experiment. With the created matrix calculations are performed, as a result of which the coefficients of the determined structure of the model are determined. Adequacy checks between the experimental and predicted values are mandatory, and once they have been completed, one can then proceed to the task set as a goal. To start the computations of the derived models, F1 for time and F2 for quality, the domain of the control parameters x1 and x2 must be discretized. In this discretization, the values of the vector from the controls x1 and x2 are determined for the corresponding address, which are substituted in the model to obtain the value for the criterion for this address. Discretization scheme of the domain by the controllers from -1 to +1 with step 1 and the values of the criteria quality and the time to make is shown. With this 3x3 discretization, the values of the two criteria were calculated. Of course, the applied discretization with only 3 nodes of the domain is only demonstrative, because it is not in a position to offer an extra. Of course, the applied discretization with only 3 nodes of the domain is only demonstrative, because it is not in a position to offer an exact analysis. The sampling density is able to determine more precisely the location of the global maximum and minimum. In the analysis of the technological processes, discrediting is chosen according to the accuracy of the used equipment. It is for this reason that the approach will be demonstrated not with 3 nodes, but with 9, or from -1 to +1 with a step of 0.25. With such a discretization, time and quality are calculated here. It is clear from the attached graphs that the model retains the nature of the dependencies observed in the experimental data for quality and fabrication time. To fulfill the objective, it is necessary to determine an effective trade-off solution between the calculated criteria, tables investigated parameters in the input control parameter space. Most often, multi-criteria are reduced to a single criteria problems, i.e., the two calculated quality and time matrices are transformed into one in which the optimization procedures are performed. The way in which the generalized matrix is constructed is defined as an optimization strategy. The complexity of the transformation problem is shown in the figure. In fact, however, the problems are much more complex and they are determined not by two but by more criteria. The second step after calculating the criteria that specifies the specified discretization is the normalization of the criteria. Normalization is a computational scaling operation for the purpose of bringing the values of the discretized criteria to a uniform scale, usually a dimensionless and uniformly percentage distributed scale. The difference between these matrices and the previous ones is that here the minimal value is assigned 0 and the maximum value is assigned 100, with all others in between recalculated relative to the specified maximum and minimum. With these recalculated matrices, the efficient solution is solved. We use the constant level contour plots shown below the matrix to visualize the solution. In cases where a problem is solved for a maximum and for one or more criteria, the condition is set in the vector solution that it takes into account the minimal value, then another transformation is made, with which the maximums figuratively become minimums and vice versa. Further, calculations are performed with this transformation. The problem we defined can be attributed to this case. The normalized values of the production time are shown on the right, and the actual values on the left, those with which the calculations will be made. Since the minimal times are desired for solving the problem, which in the maximum problem become 100, the real ones, in practice, satisfactory image quality will be sought for models providing relatively small production time values. And this will first be accomplished with a multiplicative strategy. With it, the two normalized matrices are multiplied and the address of the largest value is searched for in the newly obtained matrix, i.e. the global maximum. We choose this solution as our proposal because it is approximately the same as the pessimistic multi-criteria strategy, which was announced by us in an international journal with authors Dr. Emil Yankov, Professor Nikolai Tonchev, and Professor Lyubomir Vazov. The solution is characterized by a minimum normalized power of about 10% and a laser beam speed of about 200 to 225 millimeters per second. In order to verify the proposed mode, the additive optimization strategy was also applied. It involves optimization of a generalized matrix of the arithmetic mean values of the normalized criteria. In order to clarify the role of each of the controlling factors in the additive optimization strategy in the examination of the criteria, it is possible to introduce weighing factors. Analysis of the generalized matrix confirms that logical conclusion that Analysis of the generalized matrix confirms the logical conclusion that better quality is associated with lower beam speeds, and more productive modes require higher beam movement speeds. This is also confirmed by other weighting factors. And now, let's finish the presentation with the slide we started with. Through the optimization using moving constraints, it is possible to successfully solve multi-factor and multi-criteria problems with several iterations due to the possibility of variable step of the constraints. Dear users, this example, which had two functions, educational and promotional, clearly shows us what our computational approach actually does, in offering solutions to a very basic problem. For it, we determined a solution under different strategies after specifying all stages of the calculations. Each constant level diagram demonstrated in this presentation was preceded by corresponding calculations. Real research problems are much more complex, with many more governing parameters and criteria. But we, talking to colors, that is, with the numbers we successfully solve them. For all who have similar problems to solve, we can be available. We have the opportunity to participate in your projects and contribute to them as part of a team in our work independently of the team. To contact us, use the following addresses. Thank you very much.